cancer. It's a word we all hear, but what is it really? Well, today we're going to take a journey. We're going to start with a disease we can see and travel all the way back to the single, tiny, rogue cell where it all began. So let's dive in. Our story doesn't start in some high-tech modern lab. Nope, it starts on the dirty, soot-covered rooftops of 18th century London. There was this really observant surgeon, Sir Percival Pott, and he noticed something pretty disturbing. The young boys who worked as chimney sweeps were getting a very specific and very rare type of cancer at a shocking rate. He was the first person to make that connection, linking what they were exposed to every day, that's soot, with this terrible disease. And what Pott discovered raised a question that has driven science for centuries since. How on earth can something from the outside world, something as ordinary as soot, start a full-blown rebellion deep inside our own cells? That's the huge mystery we're going to unravel today. All right, so to understand how that rebellion gets started, we first need to know what we're actually looking for. Let's zoom out for a second and look at the big picture. The two main paths a tumor can take, benign versus malignant. Okay, so what even is a tumor? Well, at its most basic level, a tumor, or a neoplasm, is just a cluster of cells that have basically forgotten the rules. They've forgotten how to stop growing, so they just keep multiplying without any of the normal stop signs, creating this mass of rogue tissue. So here are those two distinct paths a tumor can go down. On one hand, you have benign tumors. Think of them like quiet, polite neighbors. They might get a little big, but they grow slowly, they stay in their own yard, and they generally don't cause too much trouble. Malignant tumors, what we call cancer, are the total opposite. They're like the neighbors from hell. They're aggressive, they grow fast, they invade the surrounding property, and this is the most dangerous part. They can pack up and move to a whole new neighborhood in the body. And you can literally see the difference right here. Look at the left, that's a benign tumor. See how it's this neat, round, self-contained ball? Now look at the right. That's a malignant tumor. It's just a chaotic, sprawling mess with tentacles reaching out into the tissue around it. It's the difference between an orderly line and a mosh pit. And this is the absolute key takeaway. It's this ability to spread, to metastasize. That's what makes cancer so incredibly dangerous. This is what separates a problem you can contain from a threat that can take over the entire body. So now we have a pretty good idea of what cancer is. Now let's figure out how it all happens. We're going to zoom in, way in, past the tumor, past the tissue, and right down into the command center of a single rogue cell. Believe it or not, it all starts with just one cell. Something comes along and damages its DNA, its instruction manual. Now, normally, the cell has repair crews to fix this, but for some reason, they fail. So now you have this one damaged cell that starts ignoring all the stop-growing signals, and then it starts to multiply, uncontrollably, passing on that same genetic mistake to every single one of its children. This growing family of identical, broken cells, that's what becomes a tumor. But here's the thing, it's not just any random damage. The mutations almost always hit two very specific types of genes, the ones that are in charge of controlling cell growth. The best way to think about this is to imagine the systems in a car. A car has a gas pedal and it has brakes. Well, our cells have something similar. The gas pedal is a type of gene called a proto-oncogene. Its job is to tell the cell, okay, time to grow and divide. The brakes are another kind of gene called a tumor suppressor gene. Its job is to say, whoa, hold on, time to stop growing, and it also helps repair any DNA damage. Cancer is what happens when this perfectly balanced system completely breaks down. A mutation can flip a proto-oncogene into something called an oncogene. That's like the gas pedal getting jammed to the floor. Then, at the same time, another mutation can knock out a tumor suppressor gene. That's like your brakes completely failing. So you've got a stuck accelerator and no brakes. The result is always the same, a cell in uncontrolled runaway growth. Okay, so that's the chaos happening on the inside. But what's causing that initial damage to the DNA in the first place? Well, this brings us all the way back to where we started, with Sir Percival Pott and those poor chimney sweeps. What was in all that soot? The culprits have a name. They're called carcinogens. And a carcinogen is really just anything. It could be chemical, a virus, even a type of energy that has the ability to damage a cell's DNA and kickstart those mutations that can lead to cancer. And these agents of chaos, they pretty much fall into three main buckets. You've got chemicals, which are frankly all around us, microbes, like certain viruses, and then there's radiation from both natural and man-made sources. Chemical carcinogens are everywhere. They're in tobacco smoke, they're in car exhaust, the exact kind of gunk that was in that chimney soot back in the 1700s, and they're in industrial materials like asbestos. These chemicals can get into our bodies and literally attack our DNA, scrambling the code. Then you've got microbes. Some viruses are especially sneaky. Things like HPV or hepatitis B can act like a computer virus for our cells. They literally inject their own genetic code into our DNA. This can mess up our own genes, sometimes flipping on those accelerator oncogenes or switching off the brake tumor suppressors. And finally, there's radiation. At one end of the spectrum, you've got ultraviolet radiation from the sun. Too much sun exposure can cause little kinks and breaks in our DNA, which can lead to things like skin cancer. And at the other extreme, you have high-energy ionizing radiation, like from the Chernobyl disaster, which can literally shatter our chromosomes, causing massive genetic damage and a huge spike in cancers like leukemia. So we've seen how a cancer can get started, but once it's actually there, how do doctors figure out just how serious the situation is? Well, let's take a quick look at how they assess and classify a tumor. The first step is something called grading. This is where a pathologist looks at the cancer cells under a microscope to see how much they still resemble the healthy cells they grew from. It's kind of like asking, how far have these cells strayed from their original job description? And you can see the difference so clearly here. On the left, that's a low-grade tumor. The cells are still pretty organized. They still kind of look like they're supposed to. But on the right, that's a high-grade tumor. It's just a jumbled, chaotic mess of cells that have totally lost their way. And generally, the higher the grade, the more aggressive the cancer tends to be. And after grading comes staging. So if grading is about the personality of the cancer cells, staging is all about their travel history. It answers the question, how far has this cancer spread? The most common system, TNM, looks at the size of the initial tumor, whether it spread to nearby lymph nodes, and whether it is metastasized to distant parts of the body. This entire process we've just talked about, from that very first damaged gene all the way to a full-blown tumor, it has a name. It's called oncogenesis. It's the biography of how a cancer is born. And that brings us to the biggest, most important question of all. If we know cancer is this long chain of events, this series of genetic mistakes, where's the best place to break that chain? Do we put all our effort into preventing that very first bit of DNA damage? Do we get better at detecting it super early? Or do we develop new ways to stop it from ever spreading? The answers to those questions, well, that's what will define the future of how we fight this disease. Thanks so much for joining me.